everyone. Welcome to my lab. I'm so happy you are here. I promise you a good time, especially if you pay attention. Are you ready to learn?
Yeah.
Are you ready to have fun?
Yeah.
All right. Now, what color flame do you see here?
Green.
What did you say? How about this? Does it look neat? All right, like that? In my lab, as we do experiments, we obey all the safety rules. So you notice I have my goggles on, and I also want you to see that we have a fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control, but it is part of the safety rules and regulations. So we'll put it back here. Again, as I say, ready to be used. Now, as you came in, you saw that we have on the table a whole bunch of different pieces of equipment and chemicals, but you also saw and you see now something up in the air. What do you see up in the air? What do you suppose we have in those balloons? Helium. You say helium because you know from experience that helium-filled balloons are lighter than air. These balloons have a gas in them, or maybe a mixture of gases, lighter than air. How many balloons are there?
6.
And what colors are they? See, there's 6 balloons, and they are, you said, green, yellow, and red. Is that right?
Yeah.
Actually, there are 2 that are green, 2 that are yellow, and 2 that are red, right? Not each balloon is green, yellow, and red, right? It's very important when we do scientific experiments to be accurate in the description that we go through. So, what we see in front of us here, this nice green flame, we see an example of a combustion reaction. That's a gas that burns. It's called methane. And if we spray something else on it, we get a different color of the flame. So these balloons have in them gases, and what I'm going to do is do some experiments with them. First, I'm going to light this big torch. There's even a different color flame now, right? What color is it? Yellow. Actually, if you look very closely at it, you see near the bottom there's a blue tinge. Next time you strike a match or you look at a candle, look at the beautiful yellow flame, but also look at the blue tinge near the bottom and try to think as to why there is that blue tinge near the bottom. These are all examples of reactions we call combustion reactions. They are controlled combustion reactions. Combustion is when something burns, it combines with oxygen, usually from the air. So what we're going to do is find out what's in those balloons by taking this torch and putting it up to this first balloon. Are you ready for this? Here we go. Did you see that ball of fire? You like that? That balloon had in it hydrogen, and hydrogen combines with oxygen in an explosive way. That's why you saw the ball of fire, you saw light energy, and you also heard that sound energy, right? So, as we always do in science, now we are going to repeat that experiment. So we're going to repeat the experiment, and we're going to repeat it in the dark. So may we have the lights down, please? And you're paying close attention to this. Here we go. Here comes the flame, and you like that? Were you able to see the flame better with the lights on or with the lights off? With the lights off. Let's take a look at that last explosion in slow motion. So watch the monitor and you'll be able to see the flame. You won't hear any sound, and there is the flame coming, and boom, there is that big. Isn't that neat, right? All right, so we learned from this experiment so far that hydrogen and oxygen from the air, when they combine, they explode. So let's keep going and see what will happen when I take the flame to this green balloon. Now, here we go. Whoops, what happened? That sounded like a dud, didn't it, right? But it really wasn't, because that balloon had helium in it. And helium is a gas that does not burn. It does not combine with oxygen. It does not combust. That's what we say about it. So, what we're going to do next is take a look at these 2 balloons that are up here. Now, We all obey the safety rules, and we want to protect our ears from potential damage. So I'd like each one of you to take both fingers and stick them in your ears very tightly. I can't do the experiment and protect my ears at the same time by using my fingers, so I have some earplugs. So I would like you to really protect your ears and push both fingers in. If you can hear the sound of my voice, that means you don't have your ears well protected. Now, I can't hear you back, but I can see some of you smiling. That means you heard what I said. So please protect your ears as we move on to the next experiment. And that balloon had in it a mixture of hydrogen and oxygen. There was more oxygen available to the hydrogen to combine with, and that's why we had a louder report, and that's why the combustion process was more energetic. So, what do we always do in science? Repeat the experiment. So that's what we're going to do next. Repeat the experiment, and we're going to do it in the dark. So may we have the lights down, please? And all the lights down. Here we go. Now, were you able to see the combustion reaction better with the lights on or with the lights off? With the lights off. That's something we should keep in mind whenever we are doing experiments involving the release of energy in the form of light. We should not do it outdoors in the sunlight, and if we do it indoors, we should turn the lights off. So let's take a look at that last experiment in slow motion. Once again, you will not hear the sound, but you see the flame coming close to the balloon, and a much faster reaction than we saw with just hydrogen combining with oxygen that's in the air. So we know that combustion reactions happen all the time. In fact, when a piece of wood burns, and anything that has carbon in it burns, it forms carbon dioxide. And carbon dioxide is the next chemical that we're going to look at. But before we do that, we want to take a close look at the two different balloons exploding in slow motion. So take a look at the monitor. No sound, you won't hear any sound, and you see the difference in the rates of combustion depending on how much oxygen is available for the combination with hydrogen. Well, as I was saying, when something that has carbon in it burns, it forms carbon dioxide. And what we're going to look at next is a whole bunch of experiments involving carbon dioxide. At room temperature, carbon dioxide is a gas. It has no color, so we can't see it. We say it's invisible. It has no smell, so we say it's odorless. But everyone knows about carbon dioxide because everyone knows about carbonated beverages. Carbonated beverages have in them carbon dioxide gas that is dissolved. And I'm going to do an experiment using this baby bottle. Some of you might recognize this. Except that I modified the baby bottle a little bit. In place of the nipple that has the hole in it, I have placed the rubber bulb from a medicine dropper. And this is a very strong piece of rubber. Let me try to show you how strong it is by attempting to inflate it as I blow air from my lungs into it. Here we go. It's a very strong piece of rubber. So what we're going to do, here's the experiment. Listen very carefully to this very familiar sound. You heard that? That's the release of carbon dioxide gas that's pressurized in the carbonated beverage. So I'm going to take the baby bottle and put the carbonated beverage in. Do you see anything happening there? You see bubbles. What kind of bubbles are those? They're carbon dioxide gas bubbles. That's right. And so we fill this to the top, and then I take the screw cap and I put it on tightly. What should I do next? You've done this experiment before, huh? All right, so let me shake it and see what happens. And now you can get an idea how much carbon dioxide is really dissolved in the carbonated beverage, right? it's able to inflate this very strong piece of rubber that even with the full power of my lungs and your lungs, we would not be able to inflate. So the next thing I'm going to do is try to release the pressure carefully and slowly. What happens if I'm not careful about it? It'll splash all over the place. It'll make a mess, right? So we just try to be careful about it. Oh, you like me to make a mess. I heard you laugh there, right? I'll try to be careful about it because that's, oh, I splashed a little bit, but that's all right, right? So now, carbon dioxide comes in not only the form that we just saw, carbon dioxide gas, but it also comes in a different form. And that's the next experiment that we're going to do. I have a bucket in here that has some solid in it. The solid is called dry ice. Dry ice is solid carbon dioxide. You notice I'm putting the gloves on for a reason I will tell you about in just one moment. I'm going to reach in and take some chunks of dry ice. Dry ice is solid carbon dioxide, and its temperature is minus 78 degrees Celsius. That's why I use the gloves, because if I didn't, I would get frostbite. Carbon dioxide, solid, changes to a gas directly without melting, unlike ordinary ice. The sublimation process is taking place right now. We don't see it. Why can't we see it? Because carbon dioxide gas is invisible. It's colorless, right? So we're going to do a whole bunch of experiments now with solid carbon dioxide, and I want you to focus your attention on this part of the lecture table, where in front of me I have a group of cylinders. How many do I have? 10. And are they arranged in an order of some sort or just haphazardly arranged? They seem to be arranged by the colors of the liquids that are in them, right? So I'm going to do the experiment by taking chunks of dry ice and putting them in those cylinders in a very special way. And when I get done, you tell me what that special way is, all right? What's the special way? Did I put the dry ice in every cylinder? Every other cylinder. And you see those bubbles? What are those bubbles? Carbon dioxide bubbles coming from the sublimation. You see lots of other interesting things happening too, don't you? You see color changes. What is changing color? The liquid in the cylinders where I put the dry ice is changing color, right? And those cylinders have in them dyes that we call indicators. They change color to indicate to us that a chemical reaction has taken place. Now you also see something coming off the top of each of the cylinders where I put the dry ice. What do you suppose that stuff is? What does it look like? It looks like, what did you say, smoke? It's not. No, steam is invisible. You can't see steam. And you know it's not carbon dioxide because carbon dioxide is invisible. What does it really look like? Looks like smoke. It's not smoke. It looks like fog. Yes, fog. You know what fog and clouds are? They are condensed water vapor. The water vapor is condensing on the carbon dioxide that's coming out from the sublimation process. And you notice that the condensed water vapor is moving in a downward direction. That's because carbon dioxide is heavier or denser than air. And we learned that as we watch this. And if we knew it from before, this is just a reminder that carbon dioxide is heavier and denser than air. So now I'm going to move over to the other end of the lab, and I'm going to do an experiment. This experiment I'm going to do using these empty dish pans. They're empty except for air. Air is also invisible and it's colorless. And I'm going to take some hot boiling water. I'm going to put that in the first dish pan. What do you see coming off the top? Steam is invisible, right? It's not steam, it's condensed water vapor. When it is cold outside and you blow your hand to blow your breath on your hand to warm your hand, don't tell me you see steam. What you see is condensed water vapor. So there's the condensed water vapor, and we have filled both dish pans with the boiling water. I'll put those down here, and then I have 2 buckets that have dry ice in them, and this is what we're going to do. We're going to dump the 2 buckets in here. Hello, Bucky. Welcome to my lab. I'm so happy to see you here. And I know you've been coming to my special program for many, many years. Bucky is actually a very good chemistry student. You can see that Bucky has his goggles on, right? You can also see that Bucky has a Science is Fun on button, right? So, Bucky, you have a rose that you're holding in your hand, right? We all know why Bucky is holding a rose. Why is Bucky holding a rose? Rose Bowl. We're going to the Rose Bowl this year, yes. Bucky, I have some very special experiments for you. If you would just come with me, just follow me. I'm going to show you the elements. Actually, you know, this is a chemistry lab. We talk about elements and other things. I'm going to show you the elements of success on January 1st, 1999. All right? You ready for this, Bucky? All right. I'm going to reach into my beaker right in here and pick the elements of success in the Rose Bowl on January the 1st. The first element is element number 4. And the second element is element number 85. The third element, you ready for this, Bucky? The third element is element number 92. The audience is beginning to get the idea, Bucky, and I can tell you are too. The fourth element is element number 6. And the fifth element is element number 57. That's what the badgers are going to do on the first of the year. Bucky, I know that you have final exams coming up before the Rose Bowl, and you have to study for those, right? Bucky, are you going to graduate in time? How many years does it take to graduate from... He's lifting up, let's see, 5? I have 5. Well, how many do you have, Bucky? Oh, Bucky has a different number, right? All right. So Bucky's going to graduate in 4 years. And before you graduate, Bucky, you have to study for final exams and take final exams. But is it possible by any chance, Bucky, that you can stay for the rest of this program? Do you want Bucky to stay? All right. Bucky, I have a place for you right there that I've saved for you. Yes. I'll even show you where it is. You can just, yes, there, that's where it is. Just make yourself comfortable and enjoy the rest of the festivities as we go through a whole bunch of different experiments. Now, Bucky, I want to show you and the audience another experiment. Our opponent on the 1st of January is UCLA. We're all good sports. We're all good sports. We can give them a cheer. But I want to show you what's going to happen on the 1st of January. I'm going to take this UCLA banner. I'm going to stick it in this liquid, which is clear and colorless, right? And then I'm going to take it to this burner. And that's what's going to happen to the UCLA Bruins on the 1st of January. That's what we're going to do to them. Of course, Bucky, I have our own banner, right? Here's our own banner, and I'm going to show you what that is as I take this banner, dip it into a clear and colorless liquid, and take it to the flame, and there it is on fire, but you can see the badgers are indestructible. That's what the badgers are. And we're going to destroy the Bruins, and we're going to win on the 1st of January. It's high time that we're back in the Rose Bowl, isn't it? Right? 5 years is too long, right? All right. Now, this year happens to be the sesquicentennial year of both the state of Wisconsin and the University of Wisconsin.
Ho, 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 ho! Merry Christmas! Merry Christmas, Bussa!
Merry Christmas to you, Santa. Welcome to my lab. I'm so happy to see you again. I see you got your Science is Fun button on, so you too think science is fun, don't you?
I love science.
Santa, I know this is a very busy time of the year for you, and I tried to send you a list. I wonder, did you get my list, Santa?
Oh, yes. Yes, it was a very long list.
Not really, Santa. It was just a reasonable list. Did I get what I asked for, Santa?
Well, have you been a good boy?
I've been good. Have I been good?
Ha, ha,
All right, Santa.
Oh, yes, I
I'm
have
eagerly
some-
waiting.
Some things you asked for. 4 tickets to the Rose Bowl.
4 tickets to the Rose Bowl. Oh, Bucky, those are mine. Those are mine, Bucky. Bucky, you can get in on your own, right, Bucky? 4 tickets. Oh, those are very precious. I'm going to put them in my back pocket here, Bucky. So you be careful about picking my pocket, Bucky. Right? No, Bucky, no, those are mine.
You'll need something to wear.
Yes, I got this to wear. That's good. All right.
And
Something else to wear. Oh, Santa, you're really responding to my list here. This
that'll
is
look
very
great.
nice. What do you think it is, huh? Right?
that'll look great on you.
Thank you, Santa. Thank you.
You're welcome. Now, you know, Basan, this is the University of Wisconsin's sesquicentennial year.
Indeed.
And I have a special gift for you in honor of that.
Oh, it's the special sifting and winnowing plaque that is on the side of Bascom Hall. This is the basis of academic freedom that we have at UW-Madison and at other institutions of higher education. This is very special. I recommend that everyone takes a look at this plaque and what it says because, as I say, it is the basis of what we do at our institution of higher education. Thank you so much, Santa,
You're
for
welcome.
doing this.
I also have a book for you.
Oh, this book that deals with academic freedom being on trial, it says. And I recommend this very, very highly to all people who are interested in the quality of higher education and the quality of all of education. Thank you so much,
You're
Santa,
welcome.
for
I
all
have a
this.
question for you, though.
You have a question for me?
One of my elves was having a problem with invisible ink, and I said, talk to my good friend Bassam. Did he get in contact with you?
Yes, I think we have something worked out that has to do with invisible ink, right?
Yes, invisible ink.
Yes, we have that, I think, worked out. May I show it to you?
I'd love to.
All right.
Thank you.
All right, that's invisible ink. So we have a piece of paper here that is white paper, right? So
Nothing on it.
Nothing on it. That's what you think, Santa, because I'm going to spray it with this. And there you see,
Look
we
at
have
that.
invisible ink showing up as we spray household ammonia on this
Look at
acid-base
that.
indicator.
Can I try it?
Can you try it?
Can I?
Sure, you can
Can I
try
try
it. You can try it on
let me-
this one here if you want to.
Let me try that.
All right.
Look at that.
Wonderful, Santa.
That's
See,
perfect.
That solves your problem, right?
Perfect.
Let me give you
That's
both of these. Let me give you both of these. You can take them back to your workshop and show them to your elves. Here's
My
the first
elves
one.
will love that.
Here's the first
Thank
one.
you.
And here's the second one.
I knew you could help us with that.
And the instructions on how to do this are in the back. So you just read them carefully and you'll find the instructions there. Thank you very much,
Thank you
Santa.
very much.
Merry Christmas to you, Santa, and happy holidays.
You too. Merry Christmas.
Now, here's an experiment that we can do at home. Everybody can do at home, actually. And to do this experiment, I'm going to ask someone to come out from my lab, another part of my lab, and ask, actually, Elizabeth. Elizabeth, are you ready to help with this experiment?
Yes, I am.
Please welcome Elizabeth. What do we have here?
We have some chemicals that you can just find around your house.
All right.
We have red cabbage.
Red cabbage. Put it down here.
Yeah.
Okay.
We have ammonia. We have vinegar, baking soda, detergent, lemon juice, milk, and 7-Up.
And what do we do with those?
Well, first we take the red cabbage.
Take the red cabbage. May I help with this?
Sure.
All right. What do I do with the red cabbage?
Cut off a piece,
Cut off a piece. So we need a knife. Yes.
and a cutting board. And
cutting
we also
board.
will need a blender.
We'll need a blender. All right. Maybe we can take this out of the way so I can push these back here. And cut off a piece, you said. How? About this size? Something
Yeah,
like that?
That's good. And then cut that into smaller pieces, about 2.5 centimeters.
2.5 centimeters. All right. I do this carefully so I don't cut my fingers, right?
Yeah.
Okay. So chop it again. How am I doing so far?
Very well.
All right. Okay. Next.
Next, we take it and put it in the blender.
Put it in the blender. Okay. So just put these in the blender like this.
Yep.
All right. And
And then we fill it up with water so it covers.
Covers it. Whoops, you know, there's a piece of balloon that fell in there. So I need to get that balloon piece out, right? All right, so it's out. Then did you say cover it with water?
So it covers the cabbage.
All right. Next.
Now we put the lid on.
Put the lid on, of course. Safety is very, very important. Yes.
And then we blend it.
And blend it by push the button. Enough?
That's good.
Okay.
Now
So
we need
I'm sorry?
now we need to strain it
We need to strain it, all right?
so we can separate the
We can,
cabbage
okay,
chunks.
so we need,
A strainer and
strainer.
a beaker.
right, and so what does this do now?
This separates the chunks of cabbage from the juice.
From the juice, all right. Do we need the chunk of cabbage or do we need the juice?
We need the juice.
We need the juice, so I better get rid of this here. Still dripping. So I'll just put it up here. How's that?
That's good.
All right.
And now
what?
we need to add some more water because we don't have enough cabbage juice.
All right, add some more water. I see the color stays the same.
Yeah.
All right. Is that enough?
Yeah, that's good.
Okay. Next.
Now we pour it into these glasses that you see up here.
Oh, pour it into glasses. I see.
About 1/3 of them.
About 1/3 of the glass should have
Red cabbage
red
juice.
cabbage, all right? How is that?
That's good.
That's good? I'm just eyeballing these, right? Is that good enough?
Yeah.
This looks like an interesting experiment. It's colorful so far, but it only has one color.
Well, we're going to change that.
We are, huh? Okay. All right. So, what do I do next?
Now we take the ammonia
Take the ammonia,
and pour it into the second glass.
second one, all right? Oh, neat. Very neat. All right.
Now we take some vinegar
Vinegar
and pour it into the next glass.
and vinegar and pour it into the next one. That's neat too. So what is this? Ammonia is what?
It's basic.
It's basic, so that's the color of red cabbage juice when we have something basic, and vinegar is
Acidic.
Acidic. Cool. All right, what do I do next?
Well, now we can try some other household chemicals,
All right,
like baking soda.
baking soda to find out if it's acidic or basic.
Right.
Is that the idea? All right, so I put some in here. And I can see that the color is not red, so I can make the conclusion that it is basic, right?
Right.
How about some detergent? Should I try that next?
Sure.
Okay. How do we find out if it's acidic or basic?
Well, if it's close to the color like the ammonia,
Yeah.
then it's basic.
Yeah.
And if it's close to the color like the vinegar,
Yeah.
then it's acidic.
So what should I do?
You just dump it in there.
Just dump it in there. Stop talking and just dump it in there. All right, I get the idea. So that's basic too. How about milk? Let's try milk. Because I want to find out if it's acidic or basic, right?
Okay.
Whoops, we got a problem here. The color of the milk is not letting me make a conclusion about this. So what should we really test from the household chemicals? Should we test any chemical we want, or there's something special about the chemical?
We should make sure that they're clear and their color won't interfere with the red cabbage
Oh,
juice.
so can we try this one here?
Sure.
All right, so try this one again. And I have one left, right? So I add this. I suppose this is going to be acidic, is what I would guess, because it's got carbonic acid in it. It's carbonated, so sure enough. Well, Elizabeth, thank you very much for sharing this experiment with us. I know you have other experiments that you're working on, so thank you very much for coming out to help with this.
Thank you.
Thank you.
Hey, Elizabeth, you know what happens when I shake the heck out of this can? And I give it to you to open up? What's going to happen to it?
It spews all over me.
That's right. And the reason that happens is because of something called Boyle's Law, and that's chemistry. Because when you shake this up, you create thousands of little bubbles inside the can. And when you open it up, the pressure goes down, the volume of those bubbles go up, and it spews all over you. Do you know what you do so that doesn't happen?
You tap it.
Yep, you got to tap the side of this can, because when you tap the can, you force the bubbles to the top. You open it up, the pressure still goes down. The volume of those bubbles still go up. but there's no liquid in the way, so it won't spew on you. Do you believe?
I believe.
All right, I'm going to give you this can, and all you have to do is open it up. And I'm going to keep my goggles on. I suggest you do the same, just in case. Theory guides, experiment decides. All right, here we go. Science wins!
All right, so next what we're going to do is look at an experiment that is kind of a neat and nifty experiment. It still involves dry ice, but it also involves these candles. I have, how many candles do I have here? Huh? I have about 6, you say? And trying to light them. I missed one up there, but this is a real nifty experiment. Let me just finish lighting the candles, and I'll tell you how this is going to work. We talked about carbon dioxide gas being heavier than air, right? Oh, I missed one, huh? Let's see if I can get that one up here. So, okay, I got that one. Now, to do this experiment, I need to get some more dry ice. I need the dry ice, so I put my glove on to protect my hands from the frostbite. I reach down here and get chunks of dry ice. So I put them in this flask. It has in it a clear and colorless liquid. It's actually water. I'm going to do this. As I say, this is a real nifty experiment. It requires a special fanfare, maybe even a drum roll. Can we have a drum roll, please?
Just the kind you wanted? I guess not. How you doing?
Hi. Please welcome Lee Merrick to my lab. Lee Merrick.
Hey, it's great to be here. You've already got a drum here, I see, right here.
We have a drum here, but I want to tell the audience about Lee first. Lee is a very talented chemistry teacher from Naperville High School in Illinois. He not only has received the Presidential Award for Excellence in Chemistry Teaching, but he has been, as many of you may have seen him on the David Letterman Show. He takes his students onto the David Letterman Show, and they do a lot of fun experiments. So I suppose that's what you're going to do here.
Exactly. I'm going to give you these gloves. Now, we've got some 55-gallon drum here, folks. This is the same thing you'll find in your school cafeteria. They cook the soup up the same way in a drum, just like this. It's industrial-grade soup. But instead, we've got a gallon of water in there that we're heating up.
That's on the inside?
On the inside.
All right. Shall I get in the back here?
You're going to go back there, and we're going to put some of this sealing compound on here just to make sure we get a good seal. And then we're going to close up the top. You're going to see why in a minute.
Close off the top.
Yep, you're going to put this on the top.
I want to put the, but this is hot.
I know, that's why I'm having you do it.
I see. Okay, it's really hot though.
All right, you got it on there?
I got it on.
Cool. All
right.
No hot.
More?
Now we're going to take it off.
I'll take it off.
And don't step on the burners.
Okay.
Because that's a different experiment.
All right.
And we're just going to seal this sucker off.
You're going to seal it off.
With this big honking sealing off device. Yeah, that's hot, isn't it?
Yeah, it is hot. Why are we sealing it? I don't get this.
Oh, you're going to get it in a moment.
I'm going to get it in a moment.
Literally.
All right. Okay.
All right. I think that's good.
All right. Now
we're
what?
going to put it up on this.
Put it up here.
The special can stand.
All right. Special can stand. All right.
All right. I'm going to move it back by you.
Move it back by me. All right.
And I'm going to sit right over here.
All right. I'll get out of the way then.
I don't blame you. Now we're going to do this on a small scale. I've got a pop can here that I'm going to put some water in, much like we put water in that big honker. All right, we're just going to heat the heck out of this sucker right here. Whoa, Wilbur. And what we're going to do, you're going to watch for when that white material comes out the top. What is that white stuff again? Exactly, it is condensed water vapor. It is filling up that can, just like this can is filled with that water vapor. And we're going to take this can that has now got condensed water vapor in, it's replaced a lot of the air, and we're going to turn it upside down into this beaker of water, and something interesting will happen. Whoa! Now, what happened in here, when we stuck that in there, the condensed water vapor turned back into a liquid. There wasn't very much pressure on the inside. inside it. I don't blame you guys.
Whoa, what's going on over
That's
there?
why we're back here. What happened is the water vapor on the inside of the can condensed into a liquid. There wasn't much pressure, and the atmospheric pressure pushed in and caused this can to collapse. This is the small scale version. On a larger scale, we've got the same thing going on here. We're going to cool it down with a little bit of dry ice.
Dry ice, all right.
To make it go a little bit faster.
Okay.
So that water vapor...
Wait, what do you need to handle the dry ice?
I'm not going to touch it.
You're not going to touch it. You're just going to put it on
I'm just
top.
going to put some on top.
All right.
Whoa, Wilbur. That looks like it's done. Boy, I feel depressed. So does the can.
Shall we?
Yeah, why don't you be careful. You don't want to...
Want me to handle it, right?
Yeah, that's right. I'm out of here.
You're out of here. Now you can't leave yet.
There
Whoa.
you go. Look at that can,
How about
folks.
getting your gloves on and give me a hand here, Lee? Huh?
Oh,
No,
yeah. Oh, this kind of hand. I'm sorry. I'm a
All right.
slow learner.
All right,
One,
ready? Two,
three.
Okay,
Cool.
it's out of the way. Okay. Very interesting.
Take a look at that.
Yeah. Oh, boy.
Makes a great coffee table.
Yeah.
All right, now while I get the next demonstration set up and turn off the burners, I'm going to have you.
Yes? Oh, you want me to do something here?
I'd like you to do your candlestick here.
Oh, this is how we started on this. Oh, yes.
That's right, with the
All
dry
right.
ice.
Well, I need another chunk of dry ice right here, so I'm going to put one more chunk of dry ice in this. And here's what's going to happen. I'm going to pour this downhill, and you see what the dry ice sublimation product is doing. Need a little help here, Lee.
Uh-oh.
Need a little help. Bottom one.
Bottom one?
We have too much of a draft here.
No, work.
Oh, you did it.
Work fine.
Thank you, Lee. Thank you.
We've got some big chunk of dry ice right here, a block. It has a little depression inside. And what we're going to do, we're going to put a very active metal inside this dry ice, carbon dioxide. And on top of this, this metal is magnesium. On top of it, I'm going to put some magnesium turnings.
Magnesium turnings?
That means just small pieces of magnesium, really.
I see. Okay.
And then we're going to put some powdered magnesium type material on top of that.
So magnesium and then magnesium turnings and what else?
Some powdered magnesium and an initiator, which will remain anonymous. And we're going to actually ignite this. Now keep in mind that carbon dioxide is actually used in fire extinguishers, so maybe it'll put out this magnesium fire. And I'm going to cover it or surround it with this other chunk of magnesium. We kind of had a magnesium sandwich in here, although I wouldn't want to put my tongue on it. Now, I'm going to ignite it with this study hall control device right here.
Should we look at this or what?
I wouldn't look directly at it.
wouldn't look- okay,
This is
so-
going to be so bright, brighter than Bassam right
Okay.
here.
Look at me or look at the monitor. Look at me or don't look at it directly.
Don't look at it directly
Just
because
look
the
at the
light's going to
monitor.
be very
Look
bright.
at me. All right. Either way, don't look at it directly.
All right. So I've
Anything
lit
happening?
the study hall control device. The lights are coming down.
All right.
I'm going to ignite the magnesium and step back.
I don't see anything happening. Oh, no.
I think I do.
Wow. Oh, wow.
That is white hot, folks. That is so white hot that it literally sucks the oxygen right out of the carbon dioxide. Notice that and I didn't even put my sunglasses on to see that. Now I will after the fact. You notice that it literally sucked the oxygen right out of the carbon dioxide, and then you were going to leave something on the inside that we'll take a look at in a minute. If you remove the oxygen from the carbon dioxide, what do you think you're left with? That's right, carbon. Excellent. While this is cooling down, we're going to do one more demonstration right over here with a material called thermite. Thermite is a mixture of a compound which is called iron oxide, ferric oxide. You know what iron oxide really is? It's rust. And we've got another element with it, aluminum. And it's just sitting there. The reason it's sitting there it isn't hot enough to get started. We need an initiator or activation energy. We're going to supply it with this sparkler right here. This is an exothermic reaction. Exo means out, thermic means heat. So it's going to give off a lot of heat. And in the process, the iron oxide will be transformed into iron, and the aluminum will rip the oxygen off. This is a redox reaction. You'll end up with iron at about 2,000 degrees, which is really molten iron. Well, I'm done talking about it. Let's actually do it. We're going to need the lights down for this. I'm going to light this sparkler, and I'm simply going to shove it inside here. Here we go. 1, 2. And I'm out of here. Is that cool? No, it's really hot. And in the bottom, you will see, Bassam will hold it up, the molten iron is starting to solidify again. And that sucker is red hot. All right, let's take a look and see if we can't see the carbon that's in here. I'm going to hold this up so you guys can see that, and take this very professional poking device right here, and I'm going to poke at this. Can you see the black carbon in there? Maybe you can see it on the monitor. That's cool. Okay.
Thank you, Lee. That was really spectacular.
Thanks for asking.
Thank you for coming to my lab. Thank you very much. Thanks. Now we're going to do one other experiment with carbon dioxide. We've talked about and we've seen carbon dioxide being in the gas form and also in the solid form. We're going to do this experiment by taking chunks of dry ice, and of course I need to put my glove on, right? Otherwise I'll get frostbite. And I'm going to take a few chunks of dry ice, put them in this device like so, and then I need to crush them. So I'll crush them by grinding. You notice I have my goggles on still, right? So if anything flies, it won't injure my eyes. And grind this like so, because I want to get some powdered carbon dioxide, solid carbon dioxide, powdered dry ice. Just grind it. Now, if you look at this device that is on my left, you will see that there is a gauge on top of it. I'm going to take the gauge off like this, and then I'm going to take the powdered carbon dioxide and fill this tube about a third of the way, maybe half of the way through. This powdered dry ice, like any chunk of dry ice, is undergoing the process we call sublimation. The dry ice is subliming, and even when it's powdered. So if you look carefully, you see that I have I'm almost halfway through. That's enough. Let me just take this off like this now. And I'm going to put the gauge right on, and then I'm going to tighten it. Now, this is a sealed tube. You'll be able to see, when I get done, you'll be able to see the effect of sublimation. Sublimation is taking place in a sealed tube, and this gauge is a pressure gauge. So it's going to measure a change in pressure. What number do you read now? Is it changing at all? Is the pressure going up? Right. It's going up because dry ice is subliming, changing to gaseous carbon dioxide, and it's a sealed tube. There's no escaping of the gas. And as the pressure continues to go up, the pressure builds up, something interesting is going to happen. If you keep an eye on the solid dry ice, you'll be able to see a very interesting development, as well as the continuing change in pressure. The pressure has to build up first. And as the pressure builds, is the pressure still going up? I can't see the gauge here. It's still going up? Yeah, you're nodding your head. Yes, yes. It's going. Now look carefully at what's happening. You can see the solid dry ice beginning to collapse. In fact, what's happening is that the solid dry ice under this carbon dioxide pressure is turning into liquid carbon dioxide. This is how, and now you can see it boiling. You can see bubbles coming through, right? Can you see that? And these bubbles are carbon dioxide gas bubbles, and we're forming a liquid. Can you see the liquid down there? Look carefully at what's going on in there. This is how liquid carbon dioxide is formed. So today, we've seen 3 forms of carbon dioxide: gas, liquid, and solid. And liquid carbon dioxide has a potential industrial application. It can be used, among other purposes, for cleaning. Dry cleaning is what is being contemplated as a possible use for liquid carbon dioxide. All right. This experiment we're going to do using 2 liquids that are commonly found around the house. One is household ammonia. So I'm going to put household ammonia in this one. And in the next one, I'm going to put some vinegar. And vinegar has acetic acid in it. To do this experiment, I need a device that helps me find out if these liquids conduct the electric current. So I have a light bulb. I have 2 electrodes. And of course, this is plugged into the power source. But the circuit is not complete. If we have a good conductor, such as this knife, and I touch, by the way, these electrodes are protected here with something so that if I touch them accidentally, I don't get electrocuted. The electrodes are pieces of copper. And so if I touch the bottom like this, you can see the light bulb glows very nicely. All right? So the first liquid we're going to start with is water. Water is a non-conductor of the electric current. To conduct the electric current, we need something that carries charge on it, and we don't have anything dissolved in this water. So the next one I'm going to try is household ammonia. You see, household ammonia has some ions in it, not many. It's not very bright. It has some ions in it. All right, so I'm going to go back to the water and rinse the electrodes so I don't contaminate the next liquid, which is vinegar. And we'll see if vinegar is a good conductor or just a weak conductor, as ammonia was. So here's vinegar, and we can see that vinegar is a weak conductor of the electric current. Now, I have one more beaker that has water in it. Into this beaker that has the water, and I'm going to leave that in there. I'm going to take some, what is this? Salt, table salt. And that dissolves in water, right? So I'm going to put some table salt in there, right? And I'm going to take this, rinse in between so we don't contaminate the liquids. I guess I put too much salt in there. Maybe I didn't. Let's just see. Hey, it's dissolving, right? All right, and then I take this and I put it in there, and you see that's a very good conductor of the electric current. This is the basis upon which we say liquids contain ions in large amounts if the light bulb is bright, or in smaller amounts if it isn't as bright. So the last experiment I'm going to do is actually in this. Oh, we got to rinse in between, right? We always rinse. Now I'm going to go back to the household ammonia, weak conductor, right? And I'm going to take the vinegar. I'm going to add that to it. We'll see what happens. You get a very strong conduction of the electric current. All right. I'll unplug this and put it on the side, and now ask you to focus your attention at this end of the table, where I have a colored liquid at the bottom in this beaker, and I have 4 bulbs. Let's see, 1, 2, 3, 4, 5 bulbs that are inverted that have in them a colorless gas. It's not carbon dioxide. The gas that's in there is called ammonia. Household ammonia is a water solution of the gas ammonia. Now, I'm going to take the bottom stopper here, because this is stoppered. I'm going to take this off, and you'll see why in just a second. Take the stopper off, and there's the stopper. It's off. Now, over here, there's a rubber bulb that has in it some water. I'm going to push I'm going to squeeze this to push some water to come out. You watch and see what happens as this water combines with the colorless ammonia that's out there. So here we go. Ammonia is very soluble. It dissolves in water, and as it dissolves, it lowers the pressure. And so the pressure of the atmosphere is pushing down on the surface of this liquid, and we're able to siphon it up there. And the reason we get different colors is because we have different indicators that tell us that the pH of the solution has changed. So this is a very colorful way involving ammonia, and we call this experiment the multiple ammonia fountain. Now I'd like to reach down here and get another set of flasks. And you see they have some colored liquids in them, right? And whenever we see something like this, we like to play around with it. So I'm going to take this one and shake it a little bit. How about if I shake it some more? Huh? How about this one? Shake it a little bit. Shake it some more, right? How about this one? Shake it a little bit. Ah, this only takes, shake it some more, see? Like that? In my lab, we do lots of experiments that are fun experiments, and we watch color changes, and we try to learn what causes the color to develop in the first place and why it changes. You notice that the color in the middle one has faded from what it turned out to be when I shook it. So let's shake it again. And what color is that? Right, and this one, what color is this? Yellow. What happens when I shake it? Did you see the two colors, right? So, how about this one? This one didn't fade as fast as the others. Different rates of reactions, different types of combinations of chemicals. It's just fascinating how science can be captivating to us and makes us interested in finding the answers. So, let's do another experiment. Now, to do this experiment, I'm going to call on yet another person who works in my lab, and that's Dr. Kristen Johnson. Come on out, Kristen. Please welcome Kristen. What do you have, Kristen?
Well, I saw you were shaking up some flask, and I wanted to show you an experiment that I use to shake up a flask.
All right.
So I have two clear and colorless solutions here, and of course I've got to mix them up together. And well, first of all, it turns brown, and then, gee, it looks almost black. Of course, you don't really know what's going to happen unless you shake it up.
All right.
So I'm just going to shake this up.
Well, it's black now, but it's changing color too.
Well, it is kind of changing color, isn't it?
I can see myself in it.
Well, I can see myself in it too. Can the people in the audience see themselves in it?
Wow.
Do you like that?
Yes.
Well, if you like that, I've got something even better.
What did you have in there, Kristen?
Well, I had a silver complex, and then I added a sugar solution, and the silver plated out on the inside of the glass.
And so you made some ornaments.
Some ornaments, yeah, and if you see them around town, Christmas ornaments, you'll know where they come from.
Well, thank you very much, Kristen. Thanks a lot. Thanks. So at this time, we come to the grand finale of this 29th annual special lecture, and I'm going to do this experiment in this special device that has a spiral glass tube connected to a funnel, which then has a receiving flask at the bottom. I'm going to reach down here and take two liquids. One is clear and colorless, and the other one is clear and what we're going to do in this grand finale, we're going to mix those two liquids together in the dark. So, may we have the lights off, please? All the lights down, and there we go. This is another example of a chemiluminescent reaction where the release of energy was only in the form of light. And with the lights up, please, you can see that when the light is shining on it, the house lights, then we don't have the release of energy from this chemiluminescent reaction. Well, I'd like to thank you for coming to my lab. I really enjoyed having you here. No matter what, remember, science is fun. Thank you very much. Thank you. Thanks.